All right. Another thing I want to sort of prove to you with when we're dealing with reciprocal lattices is that if we have a vector in reciprocal space and we define the indices of that vector as HKL, that is going to be normal to the HKL plane in real space, right? I've told you this is the case, but I want to show you this is the case. And so, again, if you're wanting to know where this content's coming from, it is coming from the Colody resource, Appendix 1, and again, section A1-3. Right? So that's if you want to look up additionally where this is from. So what we're going to look at is we're going to look at a plane ABC, and it is part of a plane nearest the origin in the set HKL. All right, so let me draw you again real space and kind of show you what I'm talking about here. So I'm going to define my basis vectors. So this is A, B, and C. So my plane this is my plane A, B, C. So basically those points A, B, C. So that's where I get the plane ABC. So if we think back to Miller indices, by the definition of those Miller indices, the points that we're referring to, A, B, and C, correspond to A vector over H, the B vector over K, and the C vector over L, right? So that's A, B, and C. So that's just the definition, again, reciprocals that we're talking about. So now let's consider a vector A, B. So vector from A to B, A, B, right? So we're basically thinking about, and let me change colors here so you can see it better, that vector, right, from A to B. It's a little unclear, but that's the green color there. And so we're looking at that vector AB. So if we want to think about that vector AB, we know that if we start at the point A, which is A over H, and then add the vector AB, that we get the point B. So that's the B vector over K. So that's just from start plus the vector goes to the end point, right? So nothing crazy there. But we can rearrange it to solve for the vector AB, and that is the B point minus the A point. Again, nothing crazy. This is just telling us the final point minus the end point, or sorry, the final point minus the starting point gives us the vector AB, right? That's all this is. So now we're going to look at the dot product of AB with that DHKL star vector. So in this case, the DHKL star vector, if our proof is correct, should be normal to the plane HKL. So essentially, let me change colors again. This is H. So this, if it's true, should be normal, right? And we can determine if they are normal if the dot product is equal to 0, right? So if the dot product of this and this, which is H, is 0, then those two are normal. All right, so let's see if we can prove that. All right, so I'm going to start with this written out. So DHKL star dot AB. So the AB vector is in the plane of this, right? So if we take the if we take the dot product, then they're normal. That means that this vector in the plane is normal to H, and therefore H is normal to the plane. So that's what we're doing there. And so the dot product is going to be H times A star. Or sorry, this is the definition for DHKL star. So I'm just going to write that out. And then dot the definition of AB, which we just, the vector AB, which we just came up with, which was this. All right. So when we take the dot product of this, so the dot product, we're taking H A star times minus A over H plus KB star times B over K plus LC star, and then that's 0. So this goes to 0, and so this one again, these are reciprocal, so we can use these together, and so that's when we multiply this, it's going to give us H over H, which is 1. In this case, minus, because we have that, plus, again, B and B star, we have K and over 1 over K, and so that gives us 1. So effectively, our dot product is minus 1 plus 1, and so that is 0, and we've just shown that we have the dot product 0, meaning if we go back up to this figure, this vector on the plane ABC is normal to H, and therefore that would mean that that plane is normal to H. And therefore, if we go back to the original statement, we've shown that the vector in reciprocal space with those indices is always going to be normal to HKL. So you might remember earlier on, we talked about how in cubic, if I have a plane HKL, that is normal. Sorry, if we have the direction, plane and direction in cubic, those are normal, right? But if we're talking about reciprocal space, this is always true, not just for cubic. And so that's kind of the power between the vector in reciprocal space and the plane in real space. The connection there is always true regardless of that rule.